My name is Tong from Renmin University of China. Today I'm going to introduce our work on PRED, performance-oriented random early detection for consistently stable performance in data center networks. This is a joint work with Huawei and Tsinghua University. Without any doubt, the age of large language model is coming, and it's also well studied that computation-intensive large language models demand multi-GPUs on multi-hosts. The network is more likely to become the bottleneck. This is because from CPU to GPU, from HDD to SSD, the computing and the storage performance has increased 100-fold. For example, the end-to-end latency before the improvement in computing and storage performance is on the order of 10 milliseconds. The 1 millisecond network latency is not easy to become the bottleneck. However, the end-to-end latency after the improvement in computing and storage performance, it is on the order of microseconds. The 1 millisecond network latency, including the in-network queuing, it's much easier to become the bottleneck. So to reduce the latency caused by in-network queuing, a lot of new congestion controllers have been proposed. These new algorithms have demonstrated significant improvements. However, deployment is a challenging issue. Some of them need to be deployed on hardware network interface cards or require new switches. Sometimes in some scenarios, for example, the multi-tenant data center networks, it is also difficult to modify the network protocol stack at the end host. In this case, to compensate for the above-mentioned new congestion controllers, the community also explores better in-network congestion signals. For example, the ECN. ECN is widely deployed in the data centers networks as the new congestion signal besides the packet loss. And RED, this algorithm, controls how to mark packets for ECN, has also been integrated into switches as a basic AQM. Here, we just show how the RED works. RED decides the packet marking probability according to the output queue length on the switches. Specifically, the decision-making is driven by 3 parameters: the min K, max K, and max P. When the queue length is less than the min K, no action is taken. But when the queue length is between the min K and the max K, the RED will calculate a probability according to the min K, max K, and max P with the curve. This curve is in the 2-point form. For example, the min K 0 point and the point max K and max P. When the queue length exceeds max K, then all packets are marked on the switch. Yeah, this is also well known to all the networking guys. Yeah. So, but what I want to say is that to achieve consistently high performance, these parameters, min K, max K, and max P, should be carefully configured. This is also well studied. By default, as plotted in the left figure, the curve between the min K and max K, the curve is in the 2-point form with 3 dimensions: the min K, max K, and max P. However, we argue that the point slope form is better than the 2-point form, where we calculate the slope of the line, lambda, according to max P, max K, and min K. This point slope form has less dimensions and is more interpretable. To explain this more clearly, we take the RED parameter breakdown based on a fluid model. We have this equation. The Q is the steady state Q length on the switch, and the lambda is the slope of the RED setting line. The essence of the RED settings is controlling the steady state Q length. Since lambda can monotonically influence the Q length, we think the point slope form is more interpretable. Also, we use min k lambda to replace the min k, max k, and the max p to have less dimensions to configure the RED. Other key factors affecting the Q length is, for example, the link capacity, the propagation delay, but these parameters will not be, it does not need to configure in our situations. And another factor is the flow concurrency level. It means the number of active flows in the switch. We find the larger the flow concurrency level, the larger the Q length. We can infer that if we turn the lambda, the slope, according to a fraction of n, then we can keep the Q length consistent in the case of a dynamic flow concurrency level. The motivation of this paper is RED configuration requires traffic awareness. We define the flow concurrency level as the number of active flows and the flow distribution as the distribution of flow size. We made some measurement study with different flow concurrency levels and flow distributions through both testbed and simulation. We have two interesting observations. Observation 1 is that steady state Q length grows with the number of flows. This is very easy to understand, is it? That means static RED is not suitable for dynamic flow concurrency. We also find that different concurrency levels require different slope lambda. Specifically, a larger lambda achieves better performance when the concurrency level is large and vice versa. Observation 2 is that small flows require a large steady-state Q length, while the large flows require a small steady-state Q length. This means the right RED parameter configuration highly depends on the flow distribution. For example, in the workload 1, where the small flows are dominant, we should increase the Q length, that means decrease lambda, to avoid triggering packet marking at the bottleneck switch. In the workload 2, where the large flows are dominant, then we should decrease the Q length, that means increase lambda, to avoid unnecessary Q occupancy at the bottleneck switch. Based on these observations, our first goal is that can we make the RED parameter configuration traffic aware? The state of the art, the work is ACC from the SIGCOMM 21. This ACC shares the similar high-level idea with our work, PRED. But their method is quite different. ACC uses deep reinforcement learning to take actions to configure the min k, max k, and max p according to the states of the network. However, we also find that ACC might result in long tail flow completion time, and it's not stable in some scenarios because of the impact of rapid changes in concurrent flow numbers or inaccurate predictions. Then we have the second goal. Can we make the RED parameters configuration stable? Next, we will explain how PRED can be stabilized by overcoming the following two challenges. Challenge 1 is how to bound bound the queue according to flow concurrency. The second challenge is how can the queue length adjustment be traffic aware in a stable manner? We propose the PRED, performance-oriented random early detection, to overcome the challenges. For challenge 1, how to bound queue according to flow concurrency, our answer is that we just count the number of flows directly in the switch and adjust the lambda, the slope, according to the flow concurrency in the form of MIMD. For the challenge 2, how can the queue length adjustment be traffic aware in a stable manner? Then our answer is to test and verify in small steps in the form of ARAD. Specifically, PRED uses two loosely coupled systems: the flow concurrent stabilizer, FCS, and the queue length adjuster, QLA. FCS is designed for flow concurrency adaptation, and the QLA is designed for flow distribution adaptation. In detail, FCS has two modules. The first is the flow counter. The flow counter is to count new flows and reset periodically. And the flow estimator is to estimate the concurrency or concurrent level and according to the count in multiple periods. The QLA also contains three modules. The utility function, it's just like the PCC, the congestion controller. It uses the utility function to calculate utility values within each period. And the decision maker employs the A/B testing and the two control trials to adjust PRED in AIAD. If necessary, for example, the lambda is lower than the mean K, then we further adjust mean K using a similar approach. We implement the prototype of the PRED on both Tofino 1 and the Tofino 2 switches. From our deployment experience, it is recommended that the FCS module is deployed on the data plane. But because of the resource limitation in the Tofino 1, we have to implement QLA module on the control plane. But fortunately, Tofino 2 has enough resource, then we can implement the QLA module on the data plane. This assures a faster convergence. For evaluation, we set DCTCP as the default congestion controller at the end host. We use the real workloads such as web search, data mining, and we compare PRED against a lot of schemes it's 9 schemes. For example, RED, ECN, Cordell, ECN Sharp, ACC, TCN, HPCC, FCS, and QLA. Our testbed results shows that PRED can bound steady-state queue length with dynamic flow concurrency. Our result also shows that PRED can make queue length adjustment traffic aware in a stable manner. We also conduct large-scale simulations. The results confirm that PRED can outperform other ECN or RED algorithms in real workload scenarios. Finally, we conclude this work with several takeaways. First, the essence of RED setting is controlling the steady-state queue length. We believe that the point slope form is better than the two-point form. Second, RED requires traffic awareness in terms of flow concurrency and flow distribution. We have two observations. Observation 1 is that steady-state queue length grows with the number of flows. Observation 2 is that small flows require a large steady-state queue length, while large flows require a small steady-state queue length. The discussion can be found in our paper. PRED revisits the RED parameter configuration and uses two loosely coupled systems. The FCS uses MIMD to deal with flow concurrency, and the QLA uses AIAD to deal with flow distribution. Without any modifications at the end host, and with a stable RED parameter configuration that adapts to wear to traffic dynamics, we believe that PRED has good potential to be deployed in modern production data centers. That's all for my report. Thank you very much. I will be happy to take any questions.